PCI and SICA sponsored. Big Beam 2012 contest participants from University of Missouri Kansas City and Missouri Science and Technology University at Rolla, present a video showing the design, fabrication and testing for their Big Beam. The team was sponsored by Core Slab Structures Kansas. The objective of this contest is to design and construct a precast pre-stressed concrete beam, having a desired strength capacity set forth in the rules of the competition. The team members from UMKC are Michael Eilers, Jitesh Norlagoatla, Gunjan Shatia and Kevin Buck. The team members from MS&T are Nathan Muncy and Julie Wiley. The Big Beam contest preparation was started in January 2012. The design phase took about a month. This year it was decided that simplicity of cross-section would be one of the main criteria. Based on this, some of the choices proposed were T-beam, I-beam, rectangular and inverted T. From previous years' experience, it was known that the inverted T and the I-beam would present difficulty in getting the concrete to flow well into the bottom flange even using self-compacting concrete. Therefore it was decided to design the beam as rectangular section. Strain compatibility and approximate method using ACI provisions/methodology were used for the initial design. The design was done with the help of a MATCAD file developed by Ms. Kauda Deshmukh and updated by Jitesh Norlagoatla. The method follows the provisions of ACI 318-08. It was decided that 2 pre-stressing strands would be ideal for the required capacity. The cross-section was iterated in order to minimize the cost and weight while increasing the deflection and keeping the capacity between 32 kg and 39 kg. Based on this study, it was decided to use a 7-inch by 15-inch cross-section. Finally, to reduce the weight it was decided to make a hollow core section without altering the strength capacity of the beam. 2 PVC pipes of 2-inch diameter were used to get a hollow core section of beam. Our Big Beam was fabricated at Core Slab Structures casting facility in Kansas. Steel forms of standard sizes were available at Core Slab Structures casting facility. Based on the cross-section of the beam, the formwork was planned. On the beam casting bed, the steel forms having height of 24 inches formed the 2 sides of the beam formwork, while the end forms were wooden boards of 15-inch height. To make the cross-section hollow, 2 PVC pipes were held by the end wooden board at the desired height. 0.6-inch diameter low relaxation strands were used for the pre-stressing steel. The strands were passed through the holes in the end block and held at both ends inside the pre-stressing unit. Each of the 2 strands were tensioned to 46 kits. The non-pre-stressed reinforcement was placed in the following sequence. Number 3 stirrups used for the shear reinforcement were slid under the pre-stressing strands and tied in place with ties. Then, the number 3 compression steel bars were placed at a clear height of 2 from the top by using chairs supported on the formwork. The concrete was poured through the length of the beam in a uniform manner with a transit mixer. It was then carefully vibrated along its length and corners with a needle vibrator, without disturbing the reinforcement and avoiding segregation. Top surface of the beam was made flat and smooth in order to achieve uniformity while applying the load. The pre-stressed strands were released on the 5th day after the beam casting date. The concrete strength measured on 3rd day was 81/78 SI. Before cutting the strands, the formwork was released on 3rd day. The appropriate safety measures were followed by people handling the strand release equipment. 1 strand was cut on each side at a time. 2 people, 1 at each end of beam, coordinating with each other. After the final strand was cut, the beam moved by 10-foot in longitudinal direction due to rebound caused by release of prestressed force in the strand. A minor fall occurred at one of the beam ends due to very high tensile forces being released. The testing of the big beam was performed in the High Bay Laboratory at Missouri S&T in Rolla, Missouri. The testing apparatus included 2 steel columns connected to the strong floor and attached with a primary cross beam. 2 MTS actuators were placed between the primary and secondary cross beam to apply the load to the spreader beam. The spreader beam applied the load to the big beam at the 2 desired points indicated by the permitted load configuration. The big beam was placed onto metal plates at each end to simulate a simply supported condition. This also allowed the big beam to deflect during testing. The supports were located at 8 feet from the center of the beam on each side. We marked 2 feet out from the center, on the spreader beam for loading. There were 6 by 12 by 0.5 inch plates, that 6 inches along the span of the beam for each of the loading points of the 4-point loading. Each point used a free plate sitting on a roller support. The loading was from a MTS 146 kit actuator system. The data acquisition DAQ system was 16-bit readings from the MTS for load and actuator displacement, and a 4-inch DCLVDT for reading displacement. At the center of beam, we used a plate that hung over the center of the beam to avoid drilling into the beam to mount the plates for the LVDT to push against. The LVDTs were held on separate stands next to the beam to measure the total deflection at the center. The beam was incrementally loaded at a rate of 2 kips every 30 seconds. After each 2-kip increment, the test program was paused and the beam was visually inspected for cracks. After checking for cracks and recording the results, the team prompted the test to continue loading the next 2-kip increment. The DAQ recorded LVDT readings at the center of beam and load at 1-second intervals until test was completed. The test began by loading the beam to the first 2-kip step in the program and starting the DAQ taking 1-second readings for the duration of the test. After the initial 2 kips were applied, the test was paused until the user prompted the program to continue loading. Each load point actuator delivered half of the total force, evenly dividing the force to the 2 low points. Then, the beam was incrementally loaded at a rate of 2 kips every 30 seconds.
How they roll. 4,000 pounds. Ready. £6,000. Good. Okay, 8,000 pounds, ready. I'm going to give you guys a couple of
10,000 pounds. Yep. £12,000. Yep. £14,000. Yep. £16,000.
Hey Dave, can you come over on this side? Is that just a rub mark or is it starting to crack? Right under that.
Come away from the now hit stop. Stop it quick. Thank you. See where push control and the forces are getting out of balance and we just push
The beam test was emergency stopped after about 16 kips of load had been applied due to the test setup being unbalanced. However, the beam had not been cracked at this point. It just shifted on one side. The beam test was emergency stopped after about 16 kips of load had been applied due to the test setup being unbalanced. Because of this, the teams inspected the setup and found that the beam was not loaded squarely. After this was remedied, and the beam was loaded square to the actuators, the team added sand to the top of the beam in the locations of the load plates for added test security. This masonry sand helped to ensure that there was even bearing of the load plates on the beam at those locations. After making these small changes, the test was restarted and ran smoothly using the same loading protocol.
is 2,000 pounds. Yep. Yep. How much? 8,000 pounds. Yep. £10,000. Yep. Yep. £12,000. Yep. $14,000. Yep.
16,000. Yep. $18,000. See anything? Yeah, we're good. £20,000. You guys see anything on your side? That's good. Yep. £22,000.
Check right there over that support. I saw a piece fall.
Right here?
Well, it's just not.
No, it's fall.
Okay. No cracks.
You guys okay on your side?
It's good.
Okay. Yep. Should be good. Okay. $24,000. You heard a pop?
I heard a pop, but I don't see any cracks over here. It could have been. It sounded like it was up high, so it may have been in the frame. Just a steel set. Yeah, I don't see anything over here.
Okay. You guys are good?
Good to go.
Yep.
Don't get too close, but just come through here and kind of
26,000.
This one is already. Okay. So you choose the neighbor?
Yeah. Is that one right there?
Right.
This is 3. We need a 3.
This is not neighbor.
No, it's fine. We can pick up the data.
So my side is 3. I really don't see. Because put a 2. Yep. Got one?
This one already done. You can go.
Yeah, very long, but that's it right there. What's the load? 对，那个超长，你不可能把它剪开。
但是它在有这个，看它之前有的一会儿。
First crack at 26.
Right over the support.
这是你标的是吧？
Do you have any over there?
那它就应该有的。对，签的话是。
但是我不知道是签的是I think we're good over here, Dane.
I'm good down this end.
Okay, let's right there. Yeah, we got a little one over here. Can we see your marker? So 1, 2, 3.
This one is this corner.
Yeah.
Yeah. This one is. We have.
Oh.
Another one?
Yep.
This one this one. We don't have any neighbor.
Where'd it go?
Imagine this one, this combination.
Oh, I think they did neighbor. This is YouTube. So this church is for this.
Oh, there's one. I think it's probably this. Okay, so this is one we can do. Oh, wait, I found another one, Nate.
Brian, I have a question for you. These two, they don't have a neighbor on this side, so...
You got any more? Yeah, that's about what I got on my phone. Maybe not quite that deep, but pretty close. Cool. Good to go.
Marker.
So, I go to get some neighbor in the
Eagle eye over there.
What's the load?
28,000 pounds.
Be careful.
Ain't worth it. Oh, this one propagated some more.
Ready?
Use it on. Here.
Oh, this one.
I got one, I got more here.
You put your
Else
it.
it removed now?
It'll be multicolored, at least we all got one.
This one.
Hold it, please. That's it.
This one is right now what?
What's the low, 28?
Yeah, 28.
Then we know the next one.
Okay. All right.
Yeah, because of the color. Include both of the colors.
Chapter, regular chapter.
So this is one.
Good, good. Good. You don't need it. Okay, fine. Careful. You push it one more time, please.
Not going to deep.
Yeah.
Really good.
This is China. The other one.
It's not cracking near as much as I thought it would.
No, it's not. I don't see any more on this side.
You got any of yours, are those propagating?
Yeah, I had some propagated quite a bit, like more than double the length.
Not like this. It's bigger, longer.
Made it.
Everybody good?
Burner up to 30.
Sorry.
It's okay.
Wow, that's cool to watch.
Just three. Yeah, that's the question. Amen.
The other one.
That's a little bit of five. Include this three. Yes, sir. Okay.
30,000.
Hey, you know, when this paint beam does break, it's going to go crashing to the floor. So make sure you don't get underneath the wall. Right, make sure you're plenty far away from it. No, you don't need to sit on it. You're having a lot up here.
Don't do that, dude. It's okay, it's not we're not in love.
Very much so. I think we're almost done with it. We're just getting up one. Got it.
I know that you're really good at the paper, but you've done. You're not supposed to be here. No, honestly, I really don't want to be here. I call it this and I ask you that.
It's okay.
Good over here.
You gotta take a picture of it. I'm gonna send it to Kristen.
What am I taking a picture of?
That's me. I'm gonna send it to Kristen and say, I feel your pain.
From this side?
Everybody good? Everybody clear?
From your side?
I'm gonna send this to Kristen and say, I'm going across. Testing like 40 inches.
Yeah, hey Dan, you might like not be so close now.
Okay, sorry about that. I didn't see how done it.
32,000 pounds.
Did you have one right across from you? Yeah. Yeah, that's the one I had. I was like, wow.
Do you remember what the neutral axis is on this guy? How far off the bottom?
Tell us whether we should run or not.
If the cracks get past the neutral axis, I think we're approaching it.
Yeah, I would have to say we are. Some of these are getting fairly high. Just got several. Yeah, it is. Yeah, this crack that we got over here that me and Julie just found, if you look underneath, the bottom is getting pretty.
Think it's going to give up the ghost?
Thinking that one as quickly as it propagated, and the way the bottom looks.
Dave, look at the bottom.
Oh, I know. Yeah, that's the one. That right there is.
Everybody good? Yeah. Everybody get back up.
Good.
$34,000.
Yeah, that one's going quickly. Did yours take off quickly?
No. Oh, yeah.
See that? No, if you look, the track still goes, but I use it like right there, but I don't think it stops. It's going, but I lose it right about there. Yeah, make 34.
Once it does, it'll...
You guys good?
Yeah.
Oh, yeah. 270.
Alright.
Don't worry, take a chance.
The same.
And it'll be more ductile than it won't be.
I got some shooting and screaming. Yeah, once it does.
You guys good?
Yeah.
Oh, 270.
Don't be scared. 36,000. I really don't see any need to mark any more of the cracks. Do you?
Yeah, unless it's something that would benefit.
I think we're beyond the neutral axis. It's about ready to go. So yeah, let's just keep going.
Maybe, yeah. Okay.
Yeah. Yeah.
How much?
39,000 pounds. 38,000 pounds. Correction. That's 38,000 pounds.
Breakers.
I want to hear a boom. Ready. final load? 40,000 pounds on the final load.
That's when it's only for shattered.
Good job, Gunjan.
I think that's failure.
That's definitely failure. I noticed it was getting right at 40. It couldn't make it. It wasn't making it because it was 996 and it kept pushing down into the
Trying to see what the failure was. Julie's.
I can't believe they got this. That's a compression failure. That's nice.
Yeah. Buckling. I guess I'm check the options.
Data was recorded as a data acquisition system are reported as a plot of load V/S deflection showing the initial elastic deformation followed by bent over region. The cracking load was 26 kips and peak load was 40 kips with peak deflection of 2.3 inch. Big Beam team sincerely thanks Dr. Ganesh the EDA Garajan Ph.D. P.E. Associate Professor, University of Missouri, Kansas City. Faculty Advisor for Big Beam Team, UMKC. Dr. John Myers Ph.D. P.E. Associate Professor, Missouri Science and Technology University, Rolla. Faculty Advisor Big Beam Team, MS&T. Course Lab Structures Kansas Incorporated PCI Producer Member Sponsor for Big Beam, for construction of beam. Mr. Bruno Burgess. Course Lab Structures for coordination with construction team and arranging transportation of beam to testing facility. Mr. Brian Swift. Senior Research Design Engineer, Missouri Science and Technology University, Rolla, for providing the facility for testing the beam. UMKCSC Council for Monetary Encouragement. Big Beam Contest was an excellent opportunity for me to understand the various aspects of a project. It enhanced my understanding by witnessing different stages of the project like planning, designing, construction, testing and reporting. I learned the importance of teamwork and coordination between various parties involved in the project. Also, designing the beam with necessary optimization put forth in competition rules was a very challenging task. Overall, this competition has improved my engineering skills from academic to professional level.
It is nice to get back to the basics of prestressed concrete design. The Big Beam competition serves as a learning experience for graduate students with limited prestressed design experience and as a great recapitulation of prestressed concrete flexural behavior for those with design experience in the material.
This was the first time we had performed a full load test on a large-scale concrete beam. We learned how to set up each beam for testing along with the LVDT for measuring the deflection. All programs that monitored load and deflection were set up by Missouri S&T faculty, but we were able to experience the process of how the programs functioned. I have learned the design aspects of prestressed reinforced concrete during the Big Beam Competition 2012. I have also learned working towards an efficient design with a team effort. I had an opportunity to correlate and discuss previous year's Big Beam designs. Overall, it was a great learning experience.
One actuator was experiencing more deflection when applying the same amount of load as the second actuator. This caused the secondary cross beam to torque and provide uneven load on the beam. The load had to be removed completely to allow the actuators to be adjusted. The load was then reapplied and the beam behaved as expected. The overall Big Beam test provided us with knowledge of the test setup, loading, and the behavior of the beam that was designed.
I witnessed the fabrication of prestressed concrete beam for first time, and it has motivated me to learn prestressed concrete design in detail. I could apply my knowledge of reinforced concrete design and concrete as a structural material in practice in the Big Beam project. It has enhanced my learning and helped me in stepping successfully into industry with knowledge gained from this competition.
Big Beam 2012 Team UMKC and MS&T presented this video. Thank you for watching. Video editing by Goon Jamshake.